So this idea of using an absolute value in an integral helps us connect velocity to the physical definitions of displacement and total distance traveled. The word displacement means the net distance traveled I think I've explained this to you before. I imagine net distance being like a person who's running around a track. Okay, every time they complete a lap, their net distance is 0. It looks like they haven't gone anywhere, but they'll tell you for sure that they have gone somewhere. Okay, they're feeling it in their quads and their lungs. Okay, the definition of displacement is from A to B, the parentheses of the velocity equation. So, and then that's dt, not dx anymore, but we're talking about time. So you integrate velocity to get distance, plug in the time intervals from A to B, and you'll have your displacement. Okay, the difference in that then compared to total distance, that person who's run around the track with displacement 0 has certainly traveled total distance, and so we make our definition for that using the absolute value. So it's still the integral going from A to B, but now it's the absolute value of the velocity with respect to time as its differential. Now again, you can...
So it's basically integrating the speed.
Yep. Or if you're doing it geometrically, you're doing the area under the speed graph. The area under the velocity graph. But yeah, the absolute value of velocity is speed, so we're integrating speed. So again, you can do this geometrically. You can do it with an antiderivative, but this we're going to do with our calculator. So if you'll take your calculator out, make sure that it is set into radian mode. So I want to do a little bit of everything. We did some geometry today, we did some antiderivatives, and now we're going to do some calculator work. All right, so let's start with an acceleration function. The acceleration function that we're going to work with based on time is 2t plus 16 over the quantity t plus 1 cubed. And the units on acceleration are going to be meters per second squared. Defined when time is positive, so time is greater than or equal to 0. And the initial velocity is -8 meters per second. So if that's the initial velocity, what direction is it going? Okay, it's either going to the left if this is moving side to side, or if we're talking vertically, this would be going down, okay? I didn't specify which direction we were going, so either to the left or down. So I have a couple questions to ask you about this. We're going to use our calculators and some antiderivative work to help us answer that. So first question, question A. Find v of t. So in order for us to find v of t, we need to do the antiderivative of the acceleration. So the antiderivative without bounds, because I didn't give you any ending bounds, but the antiderivative of 2t plus 16 over t plus 1 cubed, parentheses, dt. That will give us the velocity. Because we know by definition, the antiderivative of acceleration would be velocity. So the antiderivative here, you may want to rewrite this so that you have 2t plus 16 parentheses t plus 1, and that would be to the -3. It always helps me to rewrite it with a negative power when I'm working on my antiderivatives. Bless you. Okay, so the antiderivative of 2t is t squared. The antiderivative of 16, quantity t plus 1, we're going to raise our power up to -2. And then we're going to divide by the new power of -2. And then we have plus c. And that is equal to the velocity. Now how can we find our plus c? Yeah, Jeremiah. Okay, initial velocity means the assumption is the time is 0. So we're going to say the initial velocity value is -8 when time is 0. So we'll go ahead and plug in -8 for our velocity. We will plug in, I'm going to do -8, that's 16 reduced by the -2, and I'll have 0 plus 1. All right, so we simplify this, -8 equals -8 times 1 plus c. And if that's the case, then c in this case turned out to be exactly 0. Add 8 to both sides. So my velocity turned out to be t squared. I'm going to write this as -8 over the quantity t plus 1 to the -2, to the 2. So that is my velocity. All right, next question, part B. When does the particle return to its initial position? So first I asked you about an initial velocity. Now I'm asking you about initial position. And the question is, when does the particle return to its initial position? Well, like the runner who has started and done one lap and returned back to the exact initial position where they started, what do we know about that runner, or about this particle? If it's back where it started again. The displacement is 0, right. So we can assume, or we know, that the displacement is 0 in this case. So we need to set up the definition of displacement and set it equal to 0. Yeah?
We can't find position, perhaps?
We don't have enough to do a plus c. Right. Okay, so the definition of displacement is the integral from 0 to an unknown time, which we don't know yet what the time is, of our velocity function, in parentheses, not with absolute value though, just parentheses, and we need to set that equal to 0. And our velocity equation we found was t squared minus 8 over t plus 1 quantity squared, in parentheses, dt, and that is set equal to 0. So how do you solve an integral problem that's set equal to 0? This is where the graph and your calculator come in handy. Okay, we are going to graph 0 to t as a math 9, and we want to find when it equals 0 or when it crosses the x-axis, other than at 0 itself. So we know that time being 0, but that's not going to help us. Yeah, if time is 0, you haven't gone anywhere. So grab your calculators and let's put that into our y. So that time turned out to be 2.587 seconds. And that is when it returned to its initial position. All right, final question. So question C. In that same time interval, oops, can't spell. So we just found the time interval. So in that same time interval, what was the total distance? All right, so our definition of total distance is now to use the absolute value. So we want the absolute value from 0 to 2.587, so the exact same time that I just did. We know its net distance is 0, which is displacement, but what's its total difference? Distance. So you put your absolute value now around t squared minus 8 over quantity t plus 1 squared absolute value dt. And again, we'll have the calculator find that for us. All right, we'll switch back. So we get 7.587, and that's meters because of the units that were given in the original problem.